Okay, good afternoon, everyone. Yeah, in a previous presentation that we had on the Riemann tensor, so still we are talking about the Riemann tensor today, we made some conclusions and obtained some formula. One of the symmetries of the Riemann tensor we obtained then was this. Yeah, we did that sort of rigorously with some representations and transformations of the Riemann tensor. Of course, in a transformation of the Riemann tensor to show that the Riemann tensor transformed as a tensor, we obtained such an expression as this. It means also if we were to write this expression also for say r lambda, so just leaving lambda the way it is, but making some interchange here. Wherever we see nu, we put mu, we put nu. Wherever we see nu, we put k or kappa, and wherever we see kappa, we put mu. So by just some kind of cyclic permutation, we perform another cyclic permutation. Of course, these two expressions could be obtained directly from here by making these interchanges. It will be found that this also, when added together, gives 0. But by the way, we could also show this same formula from here by simply just raising the index g lambda, right? If, for instance, if I were to write g lambda alpha lambda, multiply the whole expression. Since lambda is always first on the indices on that Riemann tensor, you can see that in the end we are going to have something like r alpha, for instance, mu nu k, plus the same for the others. Of course, in the end we can change alpha everywhere all over again to lambda. And so we will have just obtained this directly from here without even making use of this expression. One other formula which we obtained then was this for the covariant derivative of the Riemann tensor in that previous presentation. And we showed what we call then to be the Bianchi identity. Again, you can see we left lambda and mu, lambda and mu, lambda and mu, but then performed the cyclic permutation of the last three indices. And so on adding the three, we obtain 0. Of course, again, we can decide to raise lambda, lambda, lambda everywhere. And then when we do that, we'll be able to obtain the Bianchi identity in this form. So you can see, of course, we have alpha, mu, alpha, mu, alpha, mu, which again I could change the alphas all to lambdas, and it will be just me raising the lambdas directly, and then the Bianchi identity will look like this. Okay, now we could also have a contracted form of the Bianchi identity by simply looking at this one here. Of course, the Bianchi identity, so we have just written this out here. We can decide to contract two indices, lambda and nu in this case, and so I simply multiply this whole expression. Okay, you can watch out for a simple change that I've made here. I think what I did was to interchange the last two indices here in this case. Yeah, for the second term. So instead of eta nu, I have here with me nu eta, and that gives us a minus sign. If you remember, it was one of the symmetries we had last time. The first two indices are odd in their permutation, the last two indices are odd. We can interchange in pairs, the first pair and last pair, and so on and so forth. So by performing that operation, I get a minus sign. I leave the other two terms just the way they are and multiply them just naively with g lambda nu. Why did I perform this operation? Because I know that when I'm contracting, for instance, we have shown that the only ways to contract is such that these are such that first and third index, and we've made that so also for this one. So that was the essence of our trying to interchange the nu and eta in the first place. Here in this case, well, they are too far off. You can see lambda here, but nu all over somewhere here. So at this point, we just settle with raising the index lambda. You can see that when we have this here multiplying this, I raise this index lambda, but then of course it becomes nu. And that's what we have here for the last term here. Okay, however, we are able to contract this Riemann tensor to get this Ricci tensor. And the same here in this case, we have been able to contract this here to obtain this Ricci tensor. So looking at this now, what we have next is we can decide also to make an interchange between the last two indices on this term, interchanging nu and kappa. And so when I do that again, I get a minus sign as one of the symmetries of the Riemann tensor. A next step also will be to contract this remaining two indices. On the first one, of course, that is what we get exactly for this one. On contracting that, we get a Ricci scalar. But of course, we can see that when we perform this operation with g mu kappa on this, what you see is that we have a mu here, but the kappa is here. There is no symmetry relating these two indices, except of course that we settle for raising mu, and of course it becomes kappa when I do so. The same also applies here. You can see in this case, actually I can contract these two indices. I can contract them as one of the symmetries or properties of the Riemann tensor. On doing that, I am left with simply the ordinary R nu, and then eta, which is left behind, semicolon nu, and of course the whole thing remains equal to 0 as usual. You can see that these two terms are the same, because kappa and kappa, nu and nu are the same. Sorry, not the same exactly, but dummy indices. So being dummy indices, we can call them whatever we like in each term. So if I decide on each term to call kappa mu, sorry, I think in this case I call them nu. So I can call this kappas nu and this nu. I could have as well call them mu. Anyway, we shall come back later to talk about that. So if I did that, I have minus this minus that, so it's minus twice of that. And this whole thing is equal to 0, so I can multiply by minus, and I'll have something like twice of this minus that. Divide both sides by 2, and this is what I get. As you can see, of course, at this point in time, this is something, well, we could try to use a trick, actually, because here we have a covariant derivative with respect to x nu, and another one with respect to x eta. So at this point in time, I can introduce a chronicle delta and look at what see what it looks like. Of course, the whole term is 0 if eta is not equal to nu, and if nu is equal to eta, then we're back here. So this is a trick just to make this index here similar to what we had here. Now, if I did that, then I can pull this covariant derivative with respect to x nu outside the bracket, and this will be equal to 0. And so I have some object in the bracket of whose covariant derivative is equal to 0. I can call this object g nu eta just because I have nu eta down. So I can call that g nu eta semicolon with respect to x nu equal to 0. This object, by the way, is called the Einstein tensor. And of course, in another variant, I can simply raise this index. Of course, that is only in this expression. If I were to multiply both sides of this expression by g mu eta, if I multiply 0 by it, I get the same 0. In doing that here, I am able to raise nu up, and I get something like g nu mu, semicolon nu, and it's the same thing as g mu nu, semicolon nu equal to 0. It's the same thing because, yeah, the Einstein tensor, okay, well, in this form of after raising, when I finish raising this index nu, what I actually obtain is what I have here in the bracket. The Ricci tensor is symmetric with respect to its indices. The metric tensor is also symmetric. So we expect also that the Einstein tensor, well, if we can call that the Einstein tensor, but this object g mu nu or g nu mu is also symmetric. That's what we've just explained by this. So g mu nu in this case is equal to that, and as we have explained, is symmetric in terms of exchange of mu and nu. So like we were saying before, that this expression, so you have here with us, this expression, covariant derivative with respect to x nu is equal to 0. It's also true when it is a covariant derivative with respect to x mu. Just as so long as it's one of the indices in this bracket. And it will still be true because like we said, starting from this place, we said we could have made both nu equal to mu and k also equal to mu. And if they are both equal to mu, then this will be mu here and this will be mu here. Then in the end, I may decide instead to multiply with g nu eta, I believe. And in the end, we are going to end up with something like this. You can just take a moment to see that what we are saying is correct, and then that will be fine. Of course, finally, as we move on, we can see that this expression equal to 0 or this equal to 0, that's either this equal to 0, that equal to 0, is called the contracted Bianchi identities. Of course, sometimes people can be so cavalier to just call it the Bianchi identities. I've been guilty of doing that once or maybe twice. So anytime you see this, people just call this Bianchi identity, but technically it's the contracted Bianchi identity. In other words, this is the contracted form of what we had here originally. So this as a point, this is one of the very important properties that we can see, or one of the results we can obtain from the Bianchi identities by employing the various symmetry properties of the Riemann tensor and also our raising operator, which is the metric tensor. So at this point, I think we will end this presentation. Hopefully we meet again for another property and symmetry properties of the Riemann tensor.